So in exercise number 2, we deal with with a problem which is similar to a problem that we solved 2 weeks ago, if I remember correctly, or 3 weeks ago. So we had the two-type Merlis model where we dealt with optimal income taxation. And what we do now in exercise 2 of problem set 2 is that we add public expenditure into the model. So everything remains basically the same compared to the model that we had in problem set 1. But what differs now is that we have a new component in the utility function. So we have this B function, which depends on the amount of the public good, which is then this small g. And yeah, we have some assumptions with respect to this function. So we assume it's continuously differentiable, strictly increasing and strictly concave. And we assume that, yeah, if there is no public good, the utility of the public good for the individuals will be 0. The rest of the exercise is quite similar to, the original problem that we had. The newest thing is that now the government does not only decide about the allocation of labor and consumption, but also about the amount of public goods which is produced. And what we are asked to do is that we should show that in the second best efficiency problem, so when the government cannot observe the ability of the individuals but only the income, so in the second best efficiency problem for this economy, the optimal amount of the public expenditure satisfies the following equality, which is then the derivative of the the marginal utility of the public good equals to the amount or the production cost of the public good here. Okay, and yes, so one thing here is one thing which you might not see immediately is that here we have a continuum of individuals, and I think in the exercise the fraction is 2/3 of them are of high type and 1/3 are of low type. It's written here, and therefore the mass of consumers is simply 1. So we do not have the situation that we had in the in proposition 1. So what we showed here in this exercise, the Samuelson condition was saying that the sum of marginal utilities for the public good must be equal to the production cost. And this is basically covered here by assuming that we have a mass of consumers equal to 1. So we have a continuum of consumers, and the mass of this consumers is equal to 1. So that's why you don't have a sum of marginal utilities being equal to the production costs here. Yeah, so just if you get confused a little bit, I hope this clarifies. Why this down here is the Samuelson condition. Okay, so since the steps are quite similar to the exercise that we covered in problem set 1, I will skip most of the steps. I will write down the general optimization problem already in the simplified, like in the almost most simplified version. So you remember we had incentive compatibility constraints, participation constraints, and I simplified them as much as possible. So I will start now at kind of a step where I simplified most of the constraints. So the problem of the government is given by the following. So the government is maximizing over the following. So it's choosing the amount of consumption for the low type, for the high type, labor of the low type, labor of the high type, and it chooses the amount of public expenditure G. And it's maximizing the following objective function, so 1/3 times the welfare function at the indirect utility function, or the utility of the individuals which have a low type, plus, I think I can fit this here, if I make this a little bit smaller, plus 2/3 times the social welfare function at the utility or evaluated at the utility of the high type. Okay, and the only difference that you can see to the objective function in the other exercise that we covered in problem set 1 is that now we have those BG functions here in the in this optimization problem. We have some constraints. So we have some constraints which must be fulfilled. So the first one being the resource constraint, which looks a little bit different now. So it's saying that the endowment in this economy, which is then labor supply basically, or income earned, weighted by the fraction of individuals with high and low ability. This is equal to the corresponding consumption of the types. But now we add the production cost of in this economy. Sorry, this should be X. So XH. And now we add G times C. Yeah, so this is the new part here. In addition, we have an incentive compatibility constraint for the high type, like an adjusted incentive compatibility constraint. So XH is equal, so XH minus YH by the power of 2 divided by 4 plus B of G is equal to XL minus YL by the power of 2 divided by 4 plus B of G. So this is ICH prime. Yeah, so I put a prime there just to show you that this is not the original incentive compatibility constraint for the high type, but it's the adjusted one where I already simplified things. So this is basically saying that the high type must be indifferent between the allocation when he is getting the high allocation or whether he's getting the low allocation. Yeah, so the low type allocation or the high type allocation or the bundle. Then we had a participation constraint for the low type, which was saying that XL minus YL by the power of 2 plus B of G must be equal to the outside utility that the low type is getting. So this is the participation constraint for the low type prime. And then we had the simplified incentive compatibility constraint for the low type, which was simply saying that the amount of income for the high type must be weakly larger than the incentive. So the income that of the low type. Okay, so this is the starting point that I'm choosing here for this exercise. But we can simplify it a little bit more. So what I will do is I will use ICH prime and PCL prime to express XH and XL as functions of YL, YH, and G. What we then have is XL is equal to U prime plus YL by the power of 2 minus B of G, and XH is equal to YH by the power of 2 divided by 4 minus YL by the power of 2 divided by 4 plus U prime plus YL by the power of 2 minus B of G. And if we plug in those expressions, so plug into an optimization problem, if we do this, we end up with the following optimization problem. Now, max over YL, YH, and G, and we max the following: 1/3 times psi of U upper bar plus 2/3 times psi of YH by the power of 2 divided by 4 minus YL by the power of 2 divided by 4 plus U upper bar plus YL by the power of 2 minus YH by the power of 2 divided by 4, such that the following condition holds, and then it's only a resource constraint which is remaining. So 1/3 times YL plus 2/3 times YH is equal to 1/3 times U upper bar plus YL by the power of 2 minus B of G plus 2/3 times YH by the power of 2 divided by 4 minus YL by the power of 2 divided by 4 plus UH plus YL by the power of 2 minus B of G and plus G times C. Okay, so this is the resource constraint if we plug in for the expressions XH and XL, which we derived by using the incentive compatibility and the participation constraint of the high and low type, respectively. Now we can bring this into Lagrangian form, and this is, I can also write this down. So in Lagrangian form, we have the following. So we max over YL, YH, G, and lambda. And we max the following. So I can copy, I think, most of the stuff here. Just do that real quick. So of course, there's no change with respect to the objective function. So this will remain the same. Then we add kind of the constraint, which is then plus delta times, and now we plug in for the constraint that we have here. So we basically do the following. Let me just copy this as well. So we, of course, there is equality here. So we just erase this, put a minus there. Oh, it should be black. And here it should be also a minus. And then there should be a final parenthesis here. Yeah, so this is the final optimization problem in Lagrangian form. And now what you can basically observe is that that's very simple now. Taking the partial derivative, with respect to G will bring us the following. So if you look into this optimization problem, what you can observe is that the only two places where G is coming into place is here and here. So it will be very simple, kind of first order condition, because what we end up with if we take the partial derivative of the Lagrangian function with respect to G is equal to the following. So delta times B prime of G minus C should be equal to 0, and therefore B prime of G is equal to C. This is the Samuelson condition, of course, considering that here we have a mass of consumers which is equal to 1. Therefore, the sum is represented by 1 times B prime of G. And this is equal to the production cost of the public good. Yeah, so this was everything with respect to exercise number 2.